Okay, let's unpack this. Welcome back to AI Paper Podcasts. Today we're digging into a really significant paper from Google Research. It's called Titans, Learning to Memorize at Test Time. This one tackles a huge problem for LLMs. How do you handle really long context efficiently without, the model forgetting everything or just breaking down? So for you, our technical audience, we're going to cut through the jargon and really understand this new memory architecture they've proposed. We'll look at how it works, the pretty surprising results, and frankly, why it might change how we think about long context from here on out.
Yeah, it's a real bottleneck right now, isn't it? You're kind of stuck. Either you have models like standard transformers that are very accurate but super expensive computationally for long stuff.
Right, that quadratic complexity nightmare.
Exactly. Or you have these efficient linear models, things like Mamba, RetNet, which are great for long sequences in theory, but they compress information so aggressively into these small states.
They end up being forgetful anyway.
Pretty much. Especially when the context gets really long. The Titans paper basically claims they found a third way.
Okay, so that's our mission today. Figure out how they built this memory system that actually learns during inference and why it's smashing benchmarks, pushing context lengths past, 2 million tokens?
Yeah, the numbers are pretty wild.
All right, let's do the quick summary first, the 1-minute version for everyone needing the highlights. So the big bottleneck is the transformer architecture itself. That self-attention mechanism we all love. It's got that ON2 time and memory complexity. Makes huge context windows basically impossible, or at least prohibitively expensive.
Right, and then the efficient guys, the linear recurrent models, they solve the ON complexity problem, which is good. But like we said, they hit this compression wall, they squash all the history into a fixed, small state.
Yeah.
And you just can't cram, an epic novel's worth of context into something tiny without losing critical details. Performance degrades badly.
Okay, enter Titans. They kind of sidestep this whole dilemma. How? They introduce this new thing called the Neural Long-Term Memory Module, or LMM.
And the key idea, the real insight here, is that this LMM acts like a meta in-context learner. It's not just a passive storage. It dynamically updates its own parameters, its weights, to memorize an abstraction of the history as it sees new tokens at test time. So during inference.
Whoa, okay, so it's learning while it's running.
Exactly. So you end up with two memory systems working together. You've got the LMM as this persistent, learning, long-term memory handling the abstractions.
And then the standard attention mechanism, maybe with a smaller window, acts as the accurate short-term working memory.
Precisely. And the results. Titans seem to outperform standard transformers and the state-of-the-art linear models like Mamba and RetNet. They scale effectively to context windows over 2 million tokens, showing much higher accuracy on those really tough retrieval and reasoning tasks.
That separation of duties sounds key. Let's dig into the thinking behind it. They mention drawing inspiration from human cognition.
Yeah, they do. They frame it in terms of neuropsychology, which is interesting. The argument is that effective learning, like in our brains, needs distinct but connected memory systems. So transformers. They're like our amazing short-term working memory. Attention is associative, it captures exact details, direct dependencies, but it's costly and fades fast, capacity limited.
And the LRMs, the linear models, they try to be the efficient long-term storage by swapping out softmax attention for some kernel function.
Right, they get the linear complexity, ON, which is what you want for scale, but they fail when the context gets truly massive.
Because of that contradiction you mentioned earlier, you need long context, but you can't squash it into a tiny fixed-size state without massive information loss.
Exactly. It's a fundamental tension. You just can't retain fidelity that way over millions of tokens.
So the paper's authors looked at the brain's separate short-term working and long-term memory systems, how they interact, and used that as a blueprint.
Conceptually, yes. That's the leap that led them to design the LMM, not just as storage, but as this meta online learner.
Okay, let's get technical. The LMM. It learns during inference. How does that actually work? What's it optimizing for?
So it's designed to learn to memorize and forget information directly into its own parameters at runtime. It essentially sees inference as an ongoing online learning problem.
And they have this cool idea based on surprise, right? Like only surprising things are worth remembering long term.
Yeah, that's the core intuition. An event that violates the model's current expectations, something surprising, is deemed more memorable.
How do you measure surprise for an LLM reading tokens?
Mathematically, they start by defining momentary surprise using the gradient of the loss function. Think of it as, how much does this new token, $6 to $, force the model to adjust given its current memory state, M2 on 29? So technically, it's based on a about error. A big gradient means a big surprise. Whoa, didn't expect that. Better update my memory.
Okay, but if you only react to the immediate surprise, couldn't you miss important stuff that comes right after a big shock, like the context flowing after the surprise?
That's a great point, and they thought of that. Relying purely on momentary surprise is brittle. So they introduced a momentum-based update rule. It's very analogous to gradient descent with momentum in training. The memory update term, let's call it STAL, gets split. Part of it depends on the momentary surprise, the gradient term, but another part depends on the past surprise, basically the update from the previous step.
So the momentum carries forward the memory of recent surprise. You're not just reacting token by token, but considering the recent trend or flow.
Exactly. It helps maintain coherence. And those factors, date and theta, are data-dependent learned gates. They let the system flexibly decide how much weight to give the immediate shock versus the ongoing context flow. Super important for handling millions of tokens.
Okay, so it's learning key value pairs using the surprise momentum dynamic. What about memory getting full? Even if it's deep, it's not infinite. How does it forget?
Crucial question. This is where adaptive forgetting comes in. The Ablation Studies showed this was incredibly important. They use another learned gate, alpha, which acts like a weight decay on the old memory state. The update looks like MEMT1, alpha MT1 plus Saint. So alpha adaptively decides how much of the old memory MT1 to keep versus how much new stuff Saint1 to integrate. It's not just kicking out the oldest stuff. It's dynamically forgetting less important or stale information based on the current context.
Prevents memory overflow intelligently.
Nice. And you mentioned the memory state itself isn't just a simple linear matrix like in some LRMs. They use deep memory.
Correct. Big difference. The LMM uses deep multi-layer perceptrons, MLPs, with like Leno 2.0 or more layers. The paper shows empirically, like in Figure 7, that deeper memory, LM3, LM44, consistently gets better perplexity than shallow LM1 or linear state models like Mamba.
Why? More expressive.
Exactly. That non-linearity allows the LMM to capture much more complex, abstract, hierarchical relationships in the data over those super long sequences. Linear compression just flattens things out too much. Now, this sounds complex. Recurrent updates, momentum, deep MLPs. Usually that means slow training, right? But they say it's parallelizable.
Yeah, that's a bit of an engineering marvel. They managed to tensorize the whole update process, the mini-batch gradient descent with momentum and weight decay. It boils down to efficient matrix multiplies and, critically, using a parallel associative scan operation.
The scan primitive. That allows calculating things like cumulative sums, or in this case, the momentum term, across a whole sequence chunk in parallel on hardware like GPUs or TPUs.
Right. Without that, training this kind of recurrent LMM would likely be way too slow to be practical.
Okay, so we have this powerful learning LMM component. Now, how did they actually integrate it into the overall model? That's where the different Titans variants come in.
Right. The Titans family architecture generally has three pieces. One is the core, which is your short-term memory, usually attention, maybe sliding window attention. Two is the long-term memory, the LMM module we just discussed. And three is something they call persistent memory, denoted Catalans. This is interesting. It's a set of learnable parameters, but they're data independent. They store general task knowledge learned during training, kind of like the model's background knowledge. It gets prepended to the input sequence.
Like a learned prompt or knowledge base.
Sort of, yeah. Okay, so the three variants differ in how they connect the core, attention, and the LMM. Let's start with the one that worked best. Memory as a context, MAC.
MAC, how does that work?
In MAC, the output state from the LMM and the persistent memory are basically just concatenated together with the current input chunk. And then this whole combined thing is fed into the attention module.
So the attention mechanism sees the current words and the long-term memory state and the persistent knowledge all at once.
Exactly. And that's powerful because attention can then dynamically decide what parts of the long-term memory are actually relevant for the current prediction. It essentially filters and integrates the memory as needed.
So attention helps manage the LMM's limited capacity by focusing on the useful bits. That makes sense why it performed best on the tricky reasoning tasks.
Yeah, it seems the most flexible integration.
Then there's memory as a gate. MAG.
Well, MAG sounds simpler.
It's structured differently. It has two branches. One is the core, say a sliding window attention SWA module handling the short-term stuff. The other is the LMM. Their outputs are then combined using a nonlinear gate.
So SWA gives precise local context, LMM gives broad historical context, and the gate learns how to mix them.
Pretty much. It's more like blending the outputs, whereas MAG lets attention look inside the memory context. MAG is conceptually clean, maybe a bit less dynamic than MIG.
And the third one, memory as a layer, MAL. This sounds like the most standard approach for hybrid models. It is. In LL, you just stack them. The output of the LMM module is fed sequentially into the SWA module, layer by layer, like passing the context baton.
How did ML do?
Interestingly, it was the least effective of the 3 variants, according to the paper.
Huh. So just layering them doesn't work as well?
Apparently not. It suggests that the real power comes from a more integrated interaction, either letting attention contextualize the memory like in MOR, or explicitly gating the outputs like in MAG. Simply stacking them seems to lose some of that synergy.
That's a really important architectural insight. Okay, let's talk results. Performance. You mentioned the LMM alone did well.
Yeah, even just the LMM module, without the attention core, outperformed other non-hybrid linear models on things like perplexity and some common sense reasoning tasks. That really validates the core ideas, the deep memory, the momentum, the adaptive forgetting.
But the real test is long context, right? Like needle in a haystack.
Absolutely. NIH is critical. And here, Titans, especially the LMM, combined with attention in the MASC setup, showed really consistent performance. They were getting over 90% accuracy even way out at 16,000 tokens context length.
While other models,
baselines like standard transformers or even other advanced models like MAMBA2 or TTT, apparently showed significant performance drops, sometimes falling off a cliff at those lengths. Either attention blew up or the compressed state lost the needle.
Okay, that's impressive. But then there's the Babylon benchmark. That one's notoriously hard, right? Multi-step reasoning over potentially millions of tokens.
Yeah, Babylon is designed to be brutal. You have to find and connect multiple facts scattered across incredibly long documents. And this is where the results get, frankly, kind of stunning. The paper reports that fine-tuned Titans, specifically the MASC variant, actually outperformed some very large models, including mentions of GPT-4 and Llama 3.17 DOB.
Wait, seriously, a potentially much smaller Titans model outperforming giants like a 70 billion parameter llama on a long context reasoning task?
That's what the results seem to indicate for this specific, very challenging benchmark.
Right.
It really underscores the point about architecture versus sheer scale.
So it's not just about having billions of parameters. If your underlying memory system can't effectively access and reason over information spread across millions of tokens.
It suggests exactly that. For tasks heavily dependent on tracking fine-grained details over extreme context lengths, a specialized dynamic memory architecture like Titan's LMM might be more crucial than it just having a massive parameter count for general knowledge. The architecture lets it use the context effectively.
That has huge implications for efficiency, right? Building capable models without needing astronomical parameter counts. Speaking of efficiency, how fast are these Titans models? Did they sacrifice speed?
No, thankfully, they maintain that linear scaling complexity. Like other linear recurrent models, Titans, LMM, and its variants show constant tokens per second throughput even as the context length grows massively. They avoid the quadratic slowdown of pure transformers.
So inference speed stays constant regardless of context length?
Pretty much, yeah. Which is essential for practical deployment with millions of tokens.
But you mentioned a trade-off earlier with the depth of the LMM.
Ah, yes. There's a trade-off within the LMM design. Making the memory deeper, using more layers in the MLP like LM4 visas and LM22, improve the model's quality, lower perplexity, better understanding. But that deeper computation does slightly decrease the training throughput, the speed at which you can train the model. So you tune that based on your needs.
And interestingly, the worst performing variant, MAL, was actually the fastest.
Yeah, because it could leverage existing highly optimized flash attention kernels for its SWA component more directly.
Yeah.
It shows that pure component speed doesn't guarantee overall model effectiveness if the architecture integrating them isn't optimal.
Fascinating. And just to close the loop on the LMM mechanics, the Ablation Studies really proved the value of those extra complexities, the momentum and forgetting.
Absolutely. They showed that removing either the momentum component, the memory of surprise flow, or the adaptive weight decay, the forgetting mechanism, led to significant performance drops. It strongly suggests that you really need these active management mechanisms for both information integration and memory pruning to make long-term memory work effectively at scale. Simple FIFO buffers or basic recurrent states just don't cut it.
Okay, so summing this all up, what's the big picture takeaway here? It feels like the Titans framework offers a really compelling path forward for the context length problem. It's efficient, it scales, And it does so by structurally separating short-term and long-term memory functions, kind of like the brain is thought to. And critically, that long-term memory isn't static, it's actively learning and forgetting during inference.
That's the essence of it. It's a structurally smarter way to handle memory. And it leads to that quote they included from Samuel Johnson: "The true art of memory is the art of attention." We saw how Titans, especially EVC, architecturally links attention, short-term focus, with LMM, long-term storage. Attention guides memory. And given that the simpler sequential MAL variant performed worse, it really makes you wonder, doesn't it? Maybe the way we connect different specialized modules in these complex AI systems, the architectural design itself, is becoming the most critical hyperparameter. It might dictate not just what the model remembers, but more importantly, how attention is allocated to effectively use and manage that memory over vast scales. Perhaps the future isn't just bigger models, but smarter connections.
A provocative thought to end on. Is architecture the new scaling frontier? Definitely something for all of us working in this space to think about. Thanks for breaking that down.
My pleasure. It's definitely exciting work.